and thank you for the opportunity to come and share some of my work with all of you. I do apologise for speaking English. I've only been in Sweden just over 3 years now, so my Swedish is not super great just yet. So I hope you will forgive me for taking it in English. I'm going to talk about some of the work that we've been doing, indeed about how we can use self-assembly in solvents to design new materials. And I thought I would tell you a couple of stories around the area of trying to design greener solvents for sustainable materials. Now, prior to being in Lund, I was in the University of Bath for 22 years, so most of this work was done at Bath, but now there is some work from my team in Lund. So I put both places on the cover slide as an acknowledgement for that. Now, you might think from looking at the title that I have terrible typing skills because the first 3 letters there are capitals. And in fact, what I was trying to show was that, it's a bit of a play on words, that I was looking at a particular type of solvent called deep eutectic systems, and that's given the abbreviation of DES, so it fits nicely for designing. And the deep eutectic systems or deep eutectic solvents are simply things where you take 2 chemicals, in this case choline chloride and urea. And choline chloride is a white solid. It has a melting point around about 300. Actually, if you heat it up to the 300, it starts to decompose before it even melts. Urea, likewise, has a melting point of about 133 degrees. But if you mix these 2 things in the right ratio, as you can see happening here, you end up with a liquid. And it's a liquid more or less at about 24 degrees, so maybe Australian room temperature, maybe not Swedish room temperature, but at least close enough to be worth thinking of it as a liquid. So what's going on? Why, if I take these 2 solids and mix them, do I get a liquid? I think this is something you're actually all very familiar with. Of course, in Sweden, when the roads freeze, you send out the gritter trucks, the trucks that spread the salt on the road. And if you mix salt and water, you get a depression of the freezing point. And so here, when you have water and salt up to about 5 molar sodium chloride, you can see that you get a decrease in the freezing point, which of course means that your roads won't freeze till you get to minus 20 degrees instead of freezing at 0. So we're looking at exactly the same phenomena here. Instead of taking salt and water and reducing the freezing point of that, we're taking our choline chloride and our urea and mixing them together. And if you look at the same sort of phase diagram for choline and urea, you can see that as I change the amount of urea, I change the depth of this melting point curve. And when you get to the right ratio here, you're at the eutectic point, which is just simply the lowest melting point. So we tend to work at ratios around here because we'd like to have a room temperature liquid. But you can also see that ratios either side of here are also likely to be liquid at room temperature. So we've got a bit of room here to play. And that is really useful because we can keep these liquids but change their properties by subtly changing the ratio of the components that we've got in it. Now, the other thing you can note here is choline. It's actually one of the B group vitamins. And urea, well, you can get that from chicken waste. Of course, it's a fertilizer, but it has a biological origin. So both of these things can be are things that you can get from sustainable or renewable sources. They don't have to come from petrochemicals. And so because it's the possibility of picking your components to make these eutectic systems from molecules which are non-petrochemical and also biodegradable, then the solvents get a label of being green and biodegradable. And they're really simple to make. You just mix them. You might have to heat them a little bit to get them to start to mix really well, but they're very easy to make. And it's been shown that they have really good solubility for things like metal oxides and drugs and various natural products from plants. okay, so that's kind of cool. We can mix two solids and get a liquid, but what do we really want to use these for? So taking a step back from our deep eutectic systems and just thinking about solvents generally. Solvents in chemistry are a huge issue. Global annual solvent usage is about 30 million tonnes a year. So that's a lot of mostly petrochemically derived materials and also a lot of waste. So if you make 1 kilogram of active pharmaceutical ingredient, study from about 2010, which is a little bit old now perhaps, but required between 10 and 800 kilograms of solvent, and on average about 46 kilograms. And so of the total mass of material that you use in making pharmaceuticals, that can be up to 80 to 90% of the material that you need before you get your drug molecule at the other end. And a lot of this actually, the solvents used in these systems, they're used because it's convenient to bring molecules together by dissolving them and mixing them in the solution, but they end up as waste. So the pharmaceutical industry waste profile in the US, this is again a bit old, 2006, but you can see the types of compounds that are used as solvents. Methanol maybe is not so bad, but dichloromethane, chloroform, hexane, all the things which are rather toxic and need to be dealt with after you've made the useful species that you actually want to use. So what can we do instead of using these toxic chemicals in synthesis? Well, there are, of course, a range of alternative solvents. Ethyl lactate from lactic acid, 2-methyl tetrahydrofuran. Both of these can be sourced from biomass, and so they can replace some of these petrochemically derived solvents. But if you look at their safety profile, they're still rather harmful, flammable, and corrosive. So if we're looking in terms of more environmentally friendly solvents, maybe, although these can be some replacements, they won't be able to improve the environmental standing of the solvents used in these sorts of industries. You can also use, of course, supercritical fluid, and that requires you to have high pressure and at least about 35 degrees C, so heating things. Industry tends not to like to have to work at high pressure if they can avoid it. It's quite expensive and, of course, also brings safety risks. And then you have ionic liquids, which are not volatile, and ionic liquids are just a type of salt. So here we have some bulky cations and some asymmetric anions that when you mix them, they just don't like to interact very directionally, and so it's very hard to get them to crystallize, so they stay as liquids. But these often involve quaternary ammonium cations, which again can be quite environmentally toxic. They also require actual synthesis to make the solvents. So we were looking at these problems with solvents and saying, well, can we do better? Can we make more environmentally friendly solvents that are bio-derived and not from petrochemicals, and that maybe have fewer bad health effects than the existing replacement green solvents? And could we perhaps make a solvent or use solvents that are functional in the reaction themselves, not just as a matrix to bring two things together? And so this is an example from the ionic liquid field where by changing the structure of the cation here, they can generate structure within the solvent. So you can see that the green parts become more and more prevalent, causing the red parts to sort of cluster. So you end up with a transition from sort of globs of green into this sponge-like phase. So we can tune the solvent properties, we can tune its polarity, what it can dissolve, and therefore try to optimize processes at the solvation level rather than the reagent level. So if I go back to my deep eutectic solvents, then I showed you the example of choline chloride and urea as a sort of archetypal deep eutectic solvent. It was one of the first ones that was really named as a solvent because it was going to be used in electrochemistry for deposition of electroplating, basically, avoiding the problems that you have with water, generating hydrogen gas at high voltages. But here you can see that this matrix is things that were reviewed in 2012 as possible deep eutectic solvents, and certainly not all of those are derived from biomass or environmentally friendly. But it is possible to choose from the vast array of chemicals out there, some that are actually biosourced and more environmentally friendly than others. So back to my choline here, which is the B vitamin. Urea, glycerol is a byproduct of the bioethanol industry, and so is sourced from plants. So the research questions that we're trying to address is, well, how do we pick? Why do we pick particular components? And can we use those components to enhance the chemistry that we're doing? And how does changing the components change the structure and the properties of these liquids? So I'm going to tell you two stories, hopefully that show that we can use these liquids in that fashion. But the first thing is, well, how do we even study a liquid structure? Normally, if you've got a crystal, you can take it, you get a crystal pattern, you can solve the structure of these materials. But a liquid is a bit different. So essentially, we can use the same techniques to study liquid structures, and my favorite techniques are liquid diffraction and small angle scattering here, which look at things on the same size range as electron diffraction or X-ray diffraction, but not in the ordered crystalline state. And here we're looking at things that are on the order of a few nanometers up to several, almost a micron, inside size, which are a bit smaller than viruses and bacteria, but carbon nanotubes or micelles or proteins are all within this size range. And one question I also often get asked is, why come to Lund? Well, you have here some of the best equipment for doing such experiments. Previously, we used to use ILL, ISIS, and diamond light source, a synchrotron. But now we've just finished an experiment at Max 4 on the weekend, and of course we're very much looking forward to the opening of ESS when it comes online in a couple of years' time. So back to my story. If I have this deep eutectic solvent structure, there was a lot of confusion at the beginning. Are they just a salt? Are they more like salt in water? What is the actual interactions between these species? So we use this neutron scattering, known as neutron total scattering on liquids, in order to try and get information about how these molecules are arranged together. Now, if you had a diffraction pattern, you've got all these nice sharp peaks, and you can index them and come up with a single structure that represents the molecule. But here, you can see we get these kind of wobbly peaks that are pretty broad, and you go, well, how on earth do you get any information out of that? Well, the nice thing about using neutrons is that we can play games with the response of the neutron to the material that we're looking at. And you can see here, this is something called the scattering length, and it's just plotted for all the elements in the first 30 elements in the periodic table. And I've labelled the interesting ones here, deuterium and hydrogen. And you can see that the scattering length is very different for these two things. So I can kind of paint my molecule by having it full of hydrogen in one case, or if I change it and make it full of deuterium in another case, then I'm going to get a very different scattering response from those two solutions. And so you can see here we've got two components, urea and choline. We've got deuterium on the choline in these two cases, hydrogen or deuterium on the urea, and vice versa for the other two cases. So it shouldn't change much about the solution if we just paint using deuterium and hydrogen. There's not much difference in the interactions or the size of those atoms. And so if we take that data, then we can build a model where we just put all of the molecules we've got in a box, and we move them around, and we keep calculating what the scattering pattern should look like until we get out something that looks like our actual data. And that gives us these sort of blobby diagrams. Now, of course, it's a liquid, so things are always moving around, and we can only really get an average structure, not a absolute, this is how it is structure. So these are sort of showing the average position. So the yellow here is the choline, the bigger molecule, and here's our chloride ions interacting with different parts of the urea. And in the choline chloride urea case, we have this sort of cage structure where everybody's participating in the structure. Everybody's part of the action. There's hydrogen bonds between all of the different parts of the structure. But if we go to choline chloride glycerol, this is not our work, but from another group doing similar experiments, they found that here, glycerol is like a big bully. It just wants to keep networks with itself, with its glycerol friends, and the choline here is sort of swept up in the glycerol network, but it doesn't interact with other cholines much at all. So really we've got these sort of chains of glycerol, and the choline's just sort of incorporated in various little spots. So if we have different components, we've got very different structures in our liquids, and that's going to give us different chemistry. Now, I started to talk to a inorganic chemist colleague called Eva Hevier. She was in Strathclyde, she's now in Bern in Switzerland. And she was doing these reactions with organometallic species, so magnesium halide and phenol or halide lithium reagents. And this is one of the sort of core reactions for making carbon-carbon bonds in organic chemistry. And she was finding that normally when you do these reactions, you do them under THF, you dry it like nothing, so there's no water anywhere because the water will react with these lithium and magnesium species. You do it under argon, so it's an inert atmosphere at minus 77 or 78 degrees Celsius to keep it cold, because these things, if you let them warm up, they just go bang and you get a fire in your lab, and nobody's very happy about that. But she found that she could do these in a little vial on the bench. You just have the vial here with your deep eutectic solvent, you put your reaction, your phenol-lithium reagent in on top, you stir like mad, takes 2 or 3 seconds, no explosions, you're in air, there's lots of water around in the air, and these things give you actually better yields than if she was doing it at minus 78 degrees C. And interestingly, she was using this choline chloride glycerol mixture, and she found that if she just used glycerol, it doesn't work at all, it just goes bang. So what is it about this solvent that is making this reaction work better than it does in normal organic solvents? And she had some theories that, if pure glycerol doesn't work, it's got to be something to do with the choline. Maybe it's interacting with my reagents and activating them somehow. So could you look at them with your techniques that look at the solvents and see what this interaction is? So we looked at them. We took this molecule, acetophenone, as our model substrate, and you can see our blobby liquid diagrams here again. And the thing to note here is that if choline is yellow, and here's our acetophenone, the choline's way out here. It's not even interacting with our species that she thinks it's activating. In fact, the acetophenone here, the thing that she wants to react, is actually bonding more with the glycerol and with the chloride than it is with this choline species. And the other thing that we found, when we tried to do these experiments, we wanted to get 2 millimoles per gram of acetophenone in our deep eutectic, but when we tried to dissolve it, we couldn't get it to dissolve. We only got about 1/5 of that concentration in the solvent. So it seemed that, well, acetophenone just wasn't very soluble in this choline chloride glycerol. It's very soluble in glycerol alone, but not so soluble in choline chloride glycerol, which is odd if it's supposed to be activating the chemical. Now, at the time, I was teaching in a colloid science course, and there's a lot of examples in colloid science where you're working with things that are sort of partially soluble. And this is going to work? Yeah, this is a demonstration that I used to do in my undergraduate teaching lectures, where you put some water in a dish, you put a bit of black pepper on top. It's mostly just so you can see what's happening. And then you introduce some molecules that are just not terribly soluble, In this case, it's dish detergent. And when you drop that in, you can see that the molecules are actually coming to the surface and pushing the pepper, even though the pepper particles are millimeters in size, but the molecules are coming to the surface and pushing the pepper out of the way. And this is something that happens a lot for partially soluble species in water, so even ethanol. If you've seen tears or if you have a glass of brandy and you see the tears rising up on the side of the glass, this is part of the same kind of effect. You're pushing the ethanol onto the surface of the water because it can't be involved in the hydrogen bonding of the water, so you end up with an enrichment at the surface. And if you have larger molecules, you get even more enrichment and self-assembly in the subphase. So my thinking was, well, if this acetophenone isn't very soluble in this deep eutectic solvent, maybe it's just getting pushed up to the surface. And what's at the surface? Well, that's where your reagent is that it can react. So to test this, we looked at these experiments where we have drops of our choline chloride glycerol, and this is pure choline chloride glycerol liquid. And when we add in our acetophenone, you can see the drop here is a bit smaller, and that's because if we have adsorption of the acetophenone onto the surface of that droplet, it's going to reduce the ability of the surface tension here to hold the weight of that droplet before it drips. So this is the biggest droplet you could make. So you can measure the change in the surface tension as you add more acetophenone into your choline chloride glycerol or pure glycerol. You see, it's very soluble in glycerol, so it just stays in the drop. It doesn't change the surface tension much at all. But in the choline chloride glycerol, it goes to the surface, changes the surface tension, and we can see that in these measurements. And to get a bit more proof, we decided to use neutron reflectivity. So again, here, neutron reflectivity is just bouncing neutrons off a surface and seeing what gets reflected back. And that tells us about the structure at the interface. If it's a clean, nice, sharp interface, we have a nice curve like this. But if we start to have layers at the interface, we get kind of wobbles in this line. So we're painting our molecules. We can paint our deep eutectic solvent components, the choline chloride and the glycerol, and we can also paint the acetophenone by putting hydrogen or deuterium on the ring here. And if you do that, you put it on a solution in the deep eutectic solvent, and here we just put an oily layer, basically a C18 monolayer, to mimic the sort of oily layer that you get when you add your reagent together into these solutions. And we could see that we got a nice layer of our acetophenone here at the interface between the deep eutectic solvent and our oil phase, suggesting that indeed the reaction was happening at the interface. And just a nice proof of this, we tried also to work with an engineer in Cambridge, Lara Taranto-Murciano, also with Eva Still, and we were looking at making the reaction in flow because that's a way to make it more efficient to go from batch into flow. So we had our deep eutectic solvent here as the continuous liquid, and we were introducing, first of all, our substrate here in toluene to make droplets, and you can see here we've got nice, well-shaped droplets. And when we add our organometallic phase here, it actually goes into the toluene phase, but then it reacts rapidly, and as it does that, it breaks up our droplets, again showing that it's gone to the interface. It's basically emulsifying the whole system for us and is acting as a surfactant in these droplets. Now, also related to the choice of solvent for these systems, when we go from batch to flow, we have our deep eutectic solvent here as the red. We're adding our substrate in as drops and then our organometallic and getting our product. And the postdoc who was working on this noticed that if you have the DES and water, everything here seems to stay more or less dissolved. And when you add the organic phase, if you add water, you start getting some cloudiness here, suggesting that the reaction byproducts, the lithium hydroxide that is made during the reaction, is not particularly soluble in water. But it is actually very soluble in the DES. And so this was nice because not only were we able to show that we could select the solvent to be slightly poorly soluble for what we want to react to make it go to the interface and react better, but we also got a solvent which now dissolves the byproducts, which means in flow that we could get no clogging of these tubes because it dissolves all the byproducts. So that was one story. The second story I just wanted to tell was about inorganic synthesis in these deep eutectic solvents. Now, for a long time, I've been interested in self-assembly and how we can use that to structure materials. And one classic example of that is using molecules like this, which have a polar part and a non-polar part. And when you put them in water, they assemble into micelles, where the polar part is on the outside interacting with the water and the tails are on the inside. And you add in a silica source, for instance, SiO2, and they interact in several different ways with these micelles, and they form these composite materials, which if you burn out the organic phase, you end up with a porous material. And that works really well for silica in water, but silica is reasonably inert. And if you'd like to make some different materials, it becomes a bit more difficult because they either react with water, they go bang, or the precursors actually change the solvent quality so you don't get any micelles forming. So we thought it'd be nice to try it with some deep eutectic solvents. Now, the first thing was, could we actually even grow oxide particles in a deep eutectic solvent? And we worked both on cerium oxide and iron oxide and showed that we could indeed grow very small nanoparticles of iron oxide, and these were used for solar water splitting to get hydrogen as a potential fuel. And we could also grow cerium oxide particles, again, very small nanoparticles in the absence of water, but with just a little bit of water, we could get these really long rod-like particles, which were very good for carbon monoxide oxidation, as you do in your car catalytic converters. So we can grow oxides. Second thing was, well, can we make the micelles? And I will cut a very long story short. Again, you can see that we get the adsorption to the interface in these deep eutectics, which allows us to see formation of, or predict that we should get formation of micelles here where the interface or tension stops changing. And then, of course, we used also small angle X-ray scattering and neutron scattering to study the size and shape of these micelles. So the answer there is yes, we can get micelles in these solvents. But when we tried to mix the two, the choline chloride urea or the choline chloride glycerol, and make our nanoparticles in the presence of the surfactants, we just got a horrible sludgy mess. But we can use a lot of different components to make these solvents. And one of the interesting components is actually a metal salt with urea. And so if you start with cerium nitrate, and this is another example of choosing our components of the solvent in a designed way. Usually they're made with chloride, but we didn't want chloride in our materials because it poisons catalysts. So we use cerium nitrate with urea. It makes a beautiful DES. It's really dense because it's got all that heavy cerium metal in it. But it looks very much like water if you think about things like surface tension and this Gordon parameter, which is a measure of potential self-assembly. So we showed that we could form micelles. Again, the surface tension gave us an indication of a critical micelle concentration, and the scattering showed us a variety of micelle shapes depending on the surfactant that we used. And in a bit of serendipity, my postdoc who was working on this was trying to make up some of these surfactant solutions, and she was a bit impatient. So what do you do when you want something to dissolve faster? You heat it up. She stuck these things in the oven, about 50, 70 degrees, not too hot. And what she found was that if she mixed at room temperature, she got a nice solution if she was prepared to hang around and wait long enough. But when she was impatient and stuck it in the oven, she got this sort of white goo. Now, fortunately, she was smart enough to think that something had actually happened here that had precipitated this cerium oxycarbonate species, because this whole solvent here is basically cerium nitrate with urea, and when you heat at 70, the urea starts to decompose and creates carbon dioxide and ammonia, which allowed it to react. And she calcined that and found that she got cerium oxide. And she had these different surfactant solutions, and you can see this is all 0.5 of a gram, but there's very different amounts in each of those vials, indicating that some of them must be quite porous. They must have a lot of air in those structures as well, not just the cerium oxide. And so in a bit of serendipity, we discovered that we could generate these porous cerium oxides just by dissolving surfactants, heating to 70, and then getting rid of the surfactant, which is a very straightforward way of generating materials. You can see here some evidence that they are actually porous, some micrographs that show that they're mostly made of disordered, compacted small crystallites of the cerium, and that they are all, in fact, the same crystalline material, in this case, after we calcined them. And the final point, we took those to our collaborator in Cambridge, who could test the CO oxidation for us. And as I said before, if we had halides present, bromine, even in our surfactant, not even in our solvent, we had really high activation energies for this reaction. So these are not very good materials. But if we used nitrate-based surfactants or non-ionic surfactants, and this nitrate surfactant here gave us the lowest activation energy, and that's one of the lowest activation energies that she had seen for these cerium oxide materials for this reaction that is in the catalytic converter. So our materials are actually pretty good. And we were quite happy about that. We'd chosen to avoid the halide in our solvent, and we could now see the benefits of that. So those were the two stories I wanted to tell. In summary, I hope I've shown you that we can do some interesting things just with molecular mixtures. These are deep eutectic solvents. We can choose the solvent components to be both green and environmentally friendly and to promote certain reactions, and we think we understand at least one reaction now, maybe not all of them. And that we can use the solvent itself to make some new interesting materials by carefully selecting the components that we use to make it. I just need to thank all of the people who actually did the work. Of course, this is not all me. My research group over many years has been involved, and my collaborator, Daniel Bauron, here at the ISIS facility, has been a long-term collaborator in these experiments to understand the structure of these solvents. Adrian and Oliver were the first two people in my group to work on deep eutectic solvent materials. Oliver did more of the solution structures, Adrian more of the self-assembly. And then it was taken up by Ria, and I talked a bit about Lara and Eva's collaboration with us, and the postdoc who did that work was Eva, and it's now being taken up by Ronak Kakadia at Lund University, particularly the cerium oxide work. So I also need to thank the instrument scientists at the ISIS and Diamond and ENSTO facilities where we did the neutron scattering work, and all of the funding agencies that are shown on the screen. And I thank you for listening.
Can you compare deep eutectic solvents with conventional eutectic solvents? How much better are deep eutectic solvents? And what is the difference in temperature?
Yeah, so obviously it depends again on the components that you pick, but the example of the urea and curling chloride, that's a melting, well, from what you would calculate if you just used the enthalpies of fusion for those compounds, the depression is 140 odd degrees Celsius. So it can be an extreme melting point depression. Other cases are not so deep. I mean, the deep refers to the difference between what you would calculate using the sort of ideal thermodynamic equations to be the eutectic melting point and what you measure in reality. And the field is still debating as to what the exact definition of deep is, but it should be substantially lower than what you would predict.
Is this
so
5 centigrades or 10 centigrades, or how much is
well, exactly. This is how do you define that? How deep should deep be? This is still something people are arguing about. From the practical point of view, I mean, there are many eutectic solvents now. For instance, if you take menthol with a fatty acid like C12 dodecanoic acid, that forms a lovely liquid. It's low viscosity, it's non-polar solvent, but the change in melting point in that mixture is maybe for 10 degrees. And so some people say, well, you should only call that a eutectic solvent, not a deep eutectic solvent. But from a practical point of view, you can use it as a solvent. So perhaps the definition is something that's nice to argue over a beer at these conferences, but if you're thinking about practicalities of using these mixtures, what you want is a good liquid range that's not changed too much. Like if you're right on the eutectic point and it's right on room temperature, choline chloride urea is actually a bit of a pain to use because in Lund it freezes overnight on the lab bench because the melting point is 24 degrees. So it would be better to have something that maybe didn't have quite such a deep eutectic, but at least if it brought the melting temperature down below room temperature, then it becomes a useful solvent. So it's sort of practicalities versus definitions here.
Thank you very much for a nice talk.
Thank you very much for an interesting lecture. I was wondering if you find a system where you have one of the components in your eutectic system, which is composed of a molecule with an asymmetric center, or a chiral molecule you use an enantiomer. Do you think you can use that for making asymmetric induction in those kind of reactions? For example, the one you showed us with alkyl or phenyl lithium and acetophenone?
Yeah, so Eva's paper does give the EE values for all of those reactions, and she does get selectivity. But using the reaction components directly, having a chiral center in them to influence the stereochemistry of the products is a really interesting topic. And there are examples for and against. And I think what it comes down to is we did the structure of a solvent with tartaric acid enantiomers in it. And it doesn't really matter which one you have if you just look at them on their own and their interactions with the choline chloride, in this case, was the other component. And if you mix them, you can see a slight difference in the rack version versus the two pure enantiomers. So I think what it's going to come down to is the interactions of those chiral components in your solvent with your reagents. If they can react or interact with your reagents such that you position them so that they can react in a selective fashion, then you will get chiral selectivity. But there's plenty of other examples in the literature where people have said, well, no, it doesn't work at all. So I think it's going to be a competition between the chiral molecule, which is part of your solvent, whatever the other pair is. Does it interact more strongly with the pair that you're making the solvent with, or does it interact more strongly with the thing that you want your substrate that you're trying to react? And I think, again, here is where knowledge of the interactions between the solvent components themselves, and then when you put a solute in, how is that solvated? Does it interact with the chiral species? And then you might get chiral selectivity. If it doesn't interact with the chiral species, then maybe you don't get such good selectivity. So I think it's possible, and there are examples in the literature from several organic groups which show it is possible, but I think you have to think about which components you choose and what the interactions are likely to be.
Yeah, thank you very much for a very fascinating talk. I was thinking, because when you presented the results here, you got it looked to me that you were very surprised about the findings when you do these mixtures. I was thinking, how much can be predicted from theoretical calculations about this?
About which? The formation of the liquids, or?
Yeah, the results you get here in general.
So there are a lot of people, I mean, obviously there are millions of chemicals and millions of potential components for these deep eutectic systems. And so computational chemists have taken on the challenge of trying to predict which components they should pick that will have these very deep changes in the eutectic melting temperature. And there are arguments, I mean, you had,
for example, the glycerol that formed this kind of sort of internal structure. You want it to be well itself, and then you added the choline chloride, and then it forms like its own little compartment. Could that be predicted?
So people are working on predicting that. So first of all, you need a good model for the interactions that two molecules are likely to have. There's a software called Cosmo RS now, which has functional group characteristics. So if you know what functional groups or what atoms you've got in your molecule and how they're put together, you can start to say, well, this part of the molecule is likely to interact with this part of the other molecule. that work is now ongoing, and there's a lot of machine learning and AI work going on in this field because the starting point is so big. And also they need experimental results like the ones we get to actually benchmark the simulations, because you can come up with a whole bunch of predictions and they can be completely false. But people are now working quite hard on building models in order to do these predictions. So it's becoming more possible. At least there's guidelines, but there's, I think, still surprises every now and again. So.
Thank you for an interesting talk. In the beginning of your talk, you're marketing these eutectic solvents as green, and some of them are from non-fossil origin. But in what other aspects are they green? Are there any applications where you use them for synthesis? Do you recycle, and how do you separate your products from the mixture?
Yeah, so again, it's going to be very much dependent on your components, but in the case of the Grignard reactions, the products generally are sufficiently hydrophobic that they separate themselves from the polar solvent, or you can just do a solvent extraction into something less polar. So you still need to use a non-polar solvent of some sort to recover the product. But I would say that there's because they're good solvents and you can adjust what is soluble in them by adjusting the components. A lot of people in the cosmetics industry now are using them to extract the latest anti-wrinkle molecule from various types of biomass, and they then do not take that molecule out of the deep eutectic solvent, but they put the whole deep eutectic solvent into their formulation, because things like glycerol are already known as skin penetration enhancers. Now, obviously, then you have to pick components of your deep eutectic solvent, not only that they're good at extracting your biomass to get this fancy molecule out that you want to put in your wrinkle cream, but you also have to then consider what you can and can't put in, skin creams from a safety point of view. But L'Oreal is a regular at all of these conferences, and I think there are several cosmetics companies now using these because they don't have to separate the active compound from the solvent, which saves them a lot of money because they don't need to do the separations. They can put it straight into their existing formulation, more or less, and being able to use it directly means that there's less waste from recovering that extracted component. If you actually are thinking about organic chemistry, there's a number of groups now, organic chemist groups, who are working on using these deep eutectic solvents, and they've come up with various strategies for recovering molecules and recycling the solvents, because a lot of, even though these components, urea is cheap, it comes from chicken poo, you don't want these things going into your wastewater. And so even if you consider that you could maybe not have to economically recycle, you still want to do that from an environmental viewpoint. So having switchable components, if you change the pH, one becomes insoluble. Things that if you can actually be quite close to their freezing point, you freeze them, and then the things that are not part of that crystalline lattice get excluded. There's a number of different strategies for getting things out of the solvents. They are not volatile, so that is good from a safety viewpoint, but it does make it harder to recover things by evaporating the solvent. So,
thank you. Nice lecture. I was looking at the vials where you had the serum dioxide with different volumes. So where you induce the voids or channels, are they ordered mesopores, or is it just random voids?
That's what Ronak's trying to do. He's trying to make the ordered ones. In the first experiments that we did on that, we actually had quite low surfactant concentrations, so we didn't expect to be in the liquid crystalline regions. And so I think that what we've done is solidified the material around isolated micelles. So we have pores, and they're connected because the material doesn't pack, it forms these tiny little crystallites. It doesn't pack that well around the micelles as it solidifies. So we get a three-dimensionally connected network, but it's not very ordered. But yeah, going up to higher concentrations of surfactant to do the liquid crystal templating, we're hoping to get the ordered structures.
Any other questions? No? In that case, thank you very, very much, Karen, for an excellent lecture and a very, very interesting topic.
Thank you.